In this video, we are going to get a better understanding of limits and how they are used in differential calculus. First, let's understand what a limit is. The limit will give a value of a function when the independent variable gets very close to a particular value. So here, let me just show a particular example on how limits can be useful. I've drawn a line that has a hole in it. If I evaluate the function at a, I will get undefined. Now limits allow us to do a little bit more. Now when I write the expression limit as x gets close to a of the function f of x, I'm looking for the independent variables to get closer and closer to a from both directions. What happens to the pertaining dependent variables? On my graph, they're going to get closer and closer to this open dot. I'm not concerned about them ever getting to the open dot, but both outputs or dependent variables are getting closer and closer to the value of b. A limit can show us some information around a hole. We're just evaluating at the point, just gives us the word undefined. Now we're going to look at another example of how limits can be useful. I've got a continuous function here. I want to look at the point that I've drawn. And particularly, I want to look at what the slope would be at that point. And the x value of that point is a. In order to get slope, we need to have a line. So in order to get a line, we need 2 points. So I'm going to go a certain distance back, we're going to call it h, and find out where the value creates a point on my function. Then I'm going to draw a line through it showing the slope between those 2 points. And that looks quite different from the slope that I would envision being at the point. So now I'm going to try a different value. I'm going to go not as far back. I'm still going to call it h just some unknown value. And I want to look at what would the slope between these 2 points be. And I draw it, and it's getting closer to what I would expect the slope at that original point to be. So now I'm showing these dots in yellow representing points that are getting closer and closer and closer to the point A. And if I drew a line through the closest yellow point I had and the original point, that line looks like it would be very, very, very close to the slope at that point. This is where limits can be useful. When the distance gets closer and closer to 0 between the 2 points, the slope of the line is approximately at that point. Another application of limits is taking another continuous function. I want to look at the area underneath the curve between 2 points. The easiest way to find area is to create rectangles. I'm breaking up region between A and B into 3 different parts, and the height of the rectangle is where that line hits the function. And I'm shading in the actual areas. And what I notice is I have an overestimation and an underestimation in each of those 3 regions. So to get a more accurate answer, I'm going to make my rectangle base smaller. Shade each one in. Each rectangle is going to have an under or an over approximation. Those are getting less and less and less. So if I could make the bases as small as possible, the height still going up to the function, those over and under approximations would get less and less and less. So this is showing you another use of limits. The limit can represent the bases of those rectangles getting smaller and smaller and smaller. And here I've written the base going to 0, and the height is just the value of the function at that input would equal the area under the curve between the values a and b. Here I've given you an understanding on how limits are very important in calculus, and hopefully this gives you a better understanding on what we're doing in this unit.